All right, so we're going to start out this lesson with an activity. We're going to learn about this thing called law of large numbers. It's actually very important that you know this theory or this idea by name. So I'm on page 7. And so we're going to talk about the probability of getting heads and talk about like the cumulative, oh, it's 8, page 8, the cumulative probability of it. All right. So first of all, theoretically, in theory, what is the probability that I'm going to get heads on a coin toss? Okay, 50%. All right. So I'm going to demonstrate an activity with my little picture up here. So this is mine. I'm going to walk you through it, and then I'm going to give you a few minutes to use your coin and do your own data and collect your own data down here at the bottom. But let's practice or understand how to do this. So first of all, when you get these fractions are going to be based on the cumulative number of heads over the number of trials that you have completed so far. Okay, so we're going to get the probability, the running tally of how many heads I have gotten so far out of the number of trials. So let me demonstrate. So I'm going to flip a coin, and I got tails. So I have now 0 heads out of 1 trial. So that's 0% right there. Okay, I'm going to flip my coin again, and I got tails again. So that is 0 heads I have gotten so far out of 2 trials. So I'm still sitting at 0%. Any ideas what I'm going to get next? I think I just got heads. Whoa. And so I have now gotten 1 heads out of 3 trials, and I'm sitting at 33 1/3%. Okay. One more. I'm going to get what? Oh, it is heads. Imagine that. So I have now gotten 2 heads out of 4 coin flips, and I am sitting at 50%, and so on. So what I want you to do is the same thing down here. So you're going to get a running total of your number of heads and do 20 trials and see where you land up. You only get 5 minutes. Actually, let's try to do it 4 minutes. So hustle, go. Okay. All right, so I did the little experiment just like you did while you were doing yours, and here's what I got. So, and man, I've done this twice today, and both times I ended at 50%. And I'm not saying that what you get, everybody's going to end at 50%, and that's not the case. Because you know what? 20 times is really not considered a whole lot of times. Many times is like hundreds and hundreds and hundreds of times. But here's the idea. And you need to know this little concept by name. And so, of course, we'll have a song of it by name. So this is called the law of large numbers. Okay, so the law of large numbers says that if you do many trials, many trials, and 20 people is not many, okay, hundreds and hundreds, then if you do many trials, many trials, then the cumulative probability will settle down to that true theoretical probability. So did yours kind of look like this? It may have started off way off from 50%, but then it settled down to somewhere close to 50%. Okay, maybe yours did that. In fact, I want to tally what yours did. So at the end, raise your hand if you had between 10 and 15% at the end of your trials, 20 to 25%, 30 to 35%. Okay, we had one of those. 40 to 45%. 1, 2, 3, 4, 5. Okay, 50 and 55%. 5, 6, 7, 8, 9, 10, 11. And I'll add myself. 7, 8, 9, 10, 11, and 12. Okay, 60 to 65%. 1, 2, 3, 4, 5, 6, 7, 8. And 70 to 75%. 70 and 75%. 80, 85%. 90, 95. Okay. So there you go. We didn't end up coming back down. We didn't have anything over here to the right, but I mean, where is this centrally located? Yeah, at the theoretical probability of 1/2. So you can see that and even if we did many, many trials, we'd even get more and more and more closer there in the middle. So let's summarize our findings. So on your notes on the next page, the first part we have already done. So you completed that law of large numbers. And so now let's talk about what's happening here. We expected the proportion of times that your penny should land on heads to be what? 1/2. What is that expected called? Like what should happen? That is theoretical probability. So this is a vocabulary term you need to know, that theoretically is what should be happening, what you expect to happen. Okay? But what happened when you did your activity? In general, what happened as you flipped the coin more and more times? The probability got what? Closer to 1/2. So in general, I mean, you don't write exactly what I have here because mine's wordy. Say something shorter like, as I flipped the coin more and more times, the probability got closer to 1/2. As you flip the coins more and more times, the overall probability got closer to 1/2. And what kind of probability was your little activity is considered? What kind of probability is that considered? It's experimental, because that's what happened in your experiment. Do you think we're interested in how far your experimental probability, what you actually got, differed from what you were expected to get, the theoretical? What is that called if we're interested in how far the actual was away from predicted? Dun, dun, dun. Residuals, which that is of interest to us, of course, always. So I love this class and how it just always spirals and connects all together. Okay, so let's take a look and kind of talk about a few things. Could you do this if, because insurance companies you take money, and then if you something happens to your home, then they'll help you pay for it. So could you, as an individual, why should you be reluctant to accept $300 payment from your neighbor with the intent on replacing their house should it burn down in the next year? Why is that not a good idea? Yeah, you're only taking in $300, okay? I mean, this is kind of like a duh question. You're only taking in $300. So now the probability that it's going to burn down is not very likely. But what happens if it does? Then, man, you are out of luck. Okay. But why can insurance companies afford to do that? Well, the probability is so low, but also what? They collect money from many, 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 many people. So they're taking in a ton of money, and it's only a few times will they have to pay out. Okay, so there is a whole career called actuarial science. One of the top statistics jobs as far as stress and money and enjoyability and blah, blah, blah. But the actuaries are the key to all the insurance rates. They are the ones who they call it actuarial tables. And they're the ones who say the probability of, say, like a male over 40 that smokes dying, or the probability that a tornado is going to come through a metropolitan area and cause this much damage, or the probability that a house in this area will burn down. So then guess what? Insurance companies set their rates based on those probabilities so that they will make a profit, even though they know that's going to happen sometimes. All right. How about this? If you're flipping a coin and your first 5 spins are heads, so you're rocking and rolling, what's the probability that that next coin flip is going to be heads? It's still 1/2. Why? because it's independent of what happened previously. All right. However, let's think about this. If you've been getting heads, and you're in a hot streak, should you bet on the next coin being heads, or should you bet on the next coin being tails because you're owed tails and it's going to level out? What do you think? Neither. Good job. You were perplexed. Neither, because that probability is still 50%, regardless of what has happened in the past and regardless of what has happened in the future. 5 times is nothing. I mean, we're talking many trials that law of large numbers is going to come out. All right, and I'll play the song for you guys of the law of large numbers later. All right, so we have one last topic. Let's go on to the next page, and we're going to get to play another game, so this will be fun. Here we go. Let's see here. All right. So next final topic is to really solidify the definitions of disjoint and independence and talk about them together. So what did we discuss yesterday is a disjoint event? They don't overlap. So you have like 2 circles. They are disjoint. They're not joined. They don't overlap. Okay, good. So those have no outcomes in common. This is supposed to say common. They have no outcomes in common. Okay, but I think it's simpler to say disjoint events can't happen at the same time. Can't happen at the same time. Okay, I think that's more kind of layman's talk. Okay, how about the definition of independent? What do we know from yesterday about and all year about independence? Beautiful. The occurrence of one event. So one event happening does not change the probability of the next event happening. Good job. Okay, so now that you have those in your brain, let's do a little game. So I have a deck of cards here, and they're well shuffled. Okay, and so Chloe's going to bet on the probability of the cards being read. Okay, and I'm going to have her pick a card and so on. Okay, so what's the probability that the card will be read when she picks one? Okay, half. We know that. All right, so she's going to pick a card and don't look at it. Okay, but give it back to me. Okay, you ready? Okay, so I'm going to give you a hint. Okay, here's a hint. You ready? It's an ace. So do you want to change your bet? What is the probability that it is read? Still 1/2. Dun, dun, dun. Okay, so discuss amongst yourselves. In fact, I want the odds to tell the evens. If picking a red and picking an ace are independent events, picking a red and picking an ace are independent based on what you know the definition is. Go. Decide and say why. Well, for later. No, like what I just did, I told you it was an ace, so it doesn't matter. I mean, okay, so what do you think? Are they independent? Yes, because the fact that I told you it's an ace does not change the probability of it being read. Okay? The fact that I told you it's an ace doesn't change the probability of it being read. Aha. Now, evens tell the odds about if if being a red and being an ace are disjoint. Go and explain why. So are they disjoint? No, why not? Because you can have a red ace. Because red and ace can happen at the same time, they are not disjoint. They're joint. Okay. All right. Very good. Let's play again. It was a black 3. Okay. All right. Okay, let's play again. Oh, Richard gets to play this time. Okay, ready? Pick a card, but don't tell me what it is. No, you can't. I mean, oh, you can't look at it. Sorry, that's what I meant. Okay, you can't look at it. Okay, ready? So, Richard, what's the probability that it's red? Okay, 1/2. Everybody, we know that. Okay. So now, so he's got a 50% chance of winning. I'm going to give you a hint. Or, yeah, I'm going to look at it and give you a hint. Okay. It's a spade. Woo! Okay, so do you want, what is your bet now? That it is probably not going to be red. So the probability that it is red is now 0. Why? Yeah, because all the spades are black. Okay, so let's flip this around. Evens tell the odds if picking a red and picking a spade are independent and why. Evens tell the odds about red and spade and independence. The fact that I told you it's a spade changed the probability of it being red. Okay, are they independent? No. Why? Because the fact that I told you it's a spade did what? Change the probability of it being red to 0. Dun, dun, dun. Okay, now we're back to the odds tell the evens. Are picking a red and picking a spade disjoint events? Picking a red and picking a spade. So this is the last one. Odds tell the evens. Are red and spade disjoint? Go. Okay, write it down. What do you think? Are they disjoint? Yes. Why? Because you cannot have a red spade. Dun, dun, dun. Okay, which, by the way, Richard, your card was a red 3. I mean, a diamond. I'm sorry, a red 3 there. A diamond 3. So, and it was red, yes. Okay, so now let's summarize what we just determined. Disjoint and independent are like 2 separate things. They're 2 separate definitions, and so they're not related. So we're tempted to say disjoint events are independent or the other way around, but we just demonstrated that is not the case. If you really look at their definitions. Okay. So that's what the deal was. So I hope that clarified disjoint and independence for you. So today we did law of large numbers, that as you do many trials, many trials, the cumulative probability, what does it do? It will settle down to that true probability, the law of large numbers you see. Okay, your homework, by the way, is pages 11 through 13, and we quiz that tomorrow. Okay, so mathematically, this 11 through 13 is nothing new mathematically than what you did last night. So hopefully you're going to feel successful with that.